Hello students, today we will discuss on the topic atomic absorption spectroscopy. Introduction. Atomic absorption spectroscopy, in short AAS, is a very common technique for detecting elements and also to determine the concentration of particular element in the samples to be analyzed. It is very reliable and simple to use. It can analyze more than 62 elements in a solution or directly in solid samples. Atomic absorption is so sensitive that it can measure down to parts per billion of a gram in a sample. The technique makes use of wavelengths of light specifically absorbed by an element. It is found to be very useful in the field of pharmacology, biophysics, and toxicology research. Coming to the principle. An atom is made up of a nucleus surrounded by electrons, and every element has a specific number of electrons which are associated with the atomic nucleus in an orbital structure which is unique to each element. The electrons occupy orbital positions in an orderly and predictable way. The lowest energy or ground state level is the normal orbital configuration for an atom, which is known to be stable electronic configuration of an atom. If energy of the right magnitude is applied to an atom, it will absorb the energy and an outer electron will be promoted to less stable configuration or excited state. This process is known as atomic absorption. Every atom has its own distinct pattern of wavelengths at which it will absorb energy. Due to the unique configuration of electrons in its outer shell. This technique uses basically the principle that free atoms, gas, generated in an atomizer can absorb the radiation or energy at specific frequency. This promotes the electrons of the atoms in the atomizer to excited state level for a short period of time. This amount of energy or wavelength is specific to a particular electron transition in a particular element, and the wavelength of light transmitted by the sample is detected, then compares them to the wavelength which originally passed through the sample. A signal processor then integrates the change in wavelength which appear in the readout as peaks of energy absorption at discrete wavelengths. The instrument is called atomic absorption spectrometer. Coming to the AAS instrumentation. The atomic absorption spectrometer consists of a light source, nebulizer, atomizer, monochromator, detector, and a data processor. Light source. An atom absorbs light at a discrete wavelength. In order to measure this narrow light absorption with maximum sensitivity, it is necessary to use a line source, which emits the specific wavelength which can be absorbed by the atom. Narrow line sources not only provide high sensitivity but also make atomic absorption a very specific analytical technique with little spectral interference. The two most common line sources used in atomic absorption are the hollow cathode lamp and the electrode-less discharge lamp. Number 1, hollow cathode lamps are the most common radiation source in atomic absorption spectrometer. It contains a tungsten anode and a hollow cylindrical cathode made of the element to be determined. These are sealed in a glass tube filled with an inert gas, that is neon or argon. Each element has its own unique lamp which must be used for that analyzer. Number 2, the electrode-less discharge lamp, in short EDL. A sealed bulb containing a small amount of the metal or salt of the element for which the source is to be used is placed inside a small self-contained RF, that is radio frequency generator or driver. When power is applied to the driver, an RF field is created. The coupled energy will vaporize and excite the atoms inside the bulb, causing them to emit their characteristic spectrum. An accessory power supply is required to operate an EDL. Electrode-less discharge lamps are typically much more intense and, in some cases, more sensitive than comparable hollow cathode lamps. They therefore offer the analytical advantages of better precision. Nebulizer. Its main purpose is to suck up the sample solution and create a fine aerosol spray. The mixture of aerosol fuel and oxidant should be mixed thoroughly for introduction into flame. Next is atomizer. In order to analyze a sample for its atomic constituents, it has to be atomized. Atomization is the separation of particles into individual molecules and breaking the molecules into atoms by exposing the samples to high temperature. This is carried out by two types of method, either by flame atomizer or graphite tube atomizer. Flame atomizer. The sample solution in aerosol form is mixed with the flame gases and conditioned in a way that only the finest aerosol droplets, less than 10 micrometer, enter the flame. In most cases, air acetylene flame with a temperature of about 2300 degrees Celsius and a nitrous oxide system N2O acetylene flame with a temperature of about 2700 degrees Celsius are commonly used. The latter flame, in addition, offers a more reducing environment, being ideally suited for analytes with high affinity to oxygen. On top of the spray chamber is a burner head that produces a flame. The radiation beam passes through this flame at its longest axis, and the flame gas flow rates may be adjusted to produce the highest concentration of free atoms. This type of atomizer is more suitable for liquid solutions or dissolved samples. Next is graphite tube atomizer or electrothermal atomizers. This type of atomizer uses a graphite-coated furnace to vaporize the samples. The samples are deposited in a small graphite-coated tube and heated to vaporize and atomize the analyte. With these techniques, liquid or dissolved, solid and the gaseous sample may be analyzed directly. This typically consists of 4 stages, such as number 1, drying. The solvent is evaporated. Second, pyrolysis. The majority of the metallic constituents are removed. Third, atomization. The analyte element is released to the gaseous phase. And fourth, cleaning. Eventually, residues in the graphite tube are removed at high temperature. Let's come to the monochromator. A monochromator is used to select the specific wavelength of light, that is spectral line, which is absorbed by the sample, and to exclude other wavelengths. The selection of the specific light allows the determination of the selected element in the presence of others. And coming to the detector. The light selected by the monochromator is directed onto a detector that is typically a photomultiplier tube. whose function is to convert the light signal into an electrical signal proportional to the light intensity. The processing of electrical signal is fulfilled by a signal amplifier. The signal be displayed for readout or further fed into a data processor for printing out by the requested format. Sample preparation. Sample preparation is often simple, and the chemical form of the element is usually unimportant. This is because atomization converts the sample into free atoms irrespective of its initial state. The sample is weighed and made into a solution by suitable dilution. Elements in biological fluids such as urine and blood are often measured simply after a dilution of the original sample. When making reference solutions of the element under analysis, for calibration, the chemical environment of the sample should be matched as closely as possible. That is, the analyte should be in the same compound and the same solvent. Teflon containers may be used when analyzing very dilute solutions because elements such as lead are sometimes leached out of the glass vessels and can affect the results. Coming to the background absorption and correction. It is possible that other atoms or molecules apart from those of the elements being determined will absorb or scatter some radiation from light source. This species could include unvaporized solvent droplets or compounds of the matrix that are not removed completely. This means that there is a background absorption as well as that of the sample. One way of measuring and correcting this background absorption is to use two light sources, one of which is the hollow cathode lamp appropriate to the element being measured. The second light source is a deuterium lamp, produces broad band radiation, not specific spectral lines as with a hollow cathode lamp. By alternating the measurements of the two light sources, generally at 50 to 100 Hz, the total absorption, that is absorption due to analyte atom plus background, is measured with a specific light from the hollow cathode lamp, and the background absorption is measured with the light from the deuterium lamp. So, by subtracting the background absorption from the total absorption gives the absorption arise from our desired analyte atoms only. Next is the determining the concentration of an element from a calibration curve. The amount of light absorbed by atoms at a characteristic wavelength can be used to measure the concentration of element in a sample. The absorbance of standard solutions with a range of concentration is measured and plotted on a graph to obtain a calibration curve by applying Beer-Lambert's law. This reduces any error due to possible variations in the atomization, efficiency and concentration and path length of the sample atoms. The unknown concentration of the atoms in the sample can then be read off once the absorbance is known. Generally, the wavelength of maximum absorbance lambda max is selected for the analysis. Let's come to the applications of atomic absorption spectroscopy. Atomic absorption spectroscopy can be used in various fields. Number 1. Environmental studies. It is used to detect the concentration of heavy metal like lead, mercury, calcium, magnesium, contamination in drinking water, ocean water and soil. And in food industry, it is used to analyze of food for nutritional content, contamination or authenticity accurately. Number 3. Pharmaceutical industry. Drug research, development and production is dependent on elemental analysis. It is necessary to test individual ingredients and continuing through production to final quality control, as impurities can affect drug efficacy and metabolism. Number 4, in petrochemical sector. From petroleum refining to a broad spectrum of applications using lubricants and oils, many industries require the determination of metals, particularly analytes that can lead to degradation and contamination, to ensure conformity as well as monitor and control processes. Number 5, chemical industrial. From the analysis of raw materials and components of finished products, testing and quality control, industrial and chemical manufacturers required accurate analytical techniques to ensure the safety and performance of their products. 6. Agriculture. Trace metals are essential for plant growth. Atomic spectroscopy also facilitates precise soil analysis to ensure that metals are not at levels that could unduly affect the food sources, that is, livestock and/or crops. Renewable energy. As the world continues to move towards eco-friendly technologies and energy resources, there's an ever-increasing need for accurate elemental analysis. Applications include testing biofuels for batch consistency and quality control, as well as trace elemental analysis on solar panels to ensure optimum performance. So here is the conclusion. Atomic absorption spectroscopy to this day has maintained a top notch in most of the academic and industrial laboratories due to its affordability and range of applications. Modern developments and advances in electronics and automation made it possible to increase laboratory applications in different areas of chemistry, such as clinical analysis of metals in biological fluids and tissues such as whole blood, plasma, urine, saliva, etc. in some pharmaceutical manufacturing processes. Minute quantities of a catalyst that remain in the final drug product, environmental analysis such as analyzing water for its metal content, industrial analysis and mining such as gold in rocks can be determined to see whether it is worth mining to extract the gold. Hence, it is very beneficial techniques. Thank you.